All right, so when we look at wavelength, there's three main components that we talk about. Frequency, which is how often we see those peaks over a certain amount of time, and then the distance between those peaks, which is the wavelength. So frequency and wavelength, which means that they have some relationship to each other. Remember the wavelength, the distance between the peaks, and how often that occurs over time, that's the frequency. And for some other reason, I guess we have to talk about the speed of light, because these radio frequencies, they are wavelengths, and they do travel at the speed of light, which in this case, they're going to use a constant of 300 million meters per second. That does seem a little bit fast. All right, and we have different characters, right? F for frequency, C for the speed of light, and then I think that's lambda, the measure in meters. And so what we look at is if I want to be able to see, and this is what they mean by inverse of understanding some of the different formulas. When we want to calculate the wavelength, I'll put the W over here, then we're going to divide the speed of light by the frequency, meaning how often the peaks occur over a certain amount of time. Or if I wanted to find the frequency, now, by the way, this is just simple algebra, right? It's the same three components. We're just looking at the different variables. And so the frequency then is going to be the speed of light divided by the wavelength. And so a better way of thinking about this without actually putting big numbers in there, and for me to try to start actually doing math with 300 million in front of you, is that we could say that the higher the frequency of a signal, then the smaller the wavelength of that signal. So think about it. So we're taking, all right, I just promised not to do this math, but I'm going to have to, just to help make sense of this. So if the first formula for wavelength, right, it says the higher the frequency, the smaller the wavelength. So, if I have this speed of light, as f gets bigger, I mean, think about it. If I were to divide this by 10 for the frequency, and I'm just picking out numbers that we actually wouldn't use, they'd be much bigger numbers. But you can see that the higher this gets, right, the smaller the wavelength, a smaller number, right? That's basically showing you that as I have more frequency, I mean, now if I were to do that division here, I'd be taking off a bunch of these zeros. And so the wavelength is going to be smaller. Now, on the other side, when I'm looking at the frequency, and I take, let's say, that 300 million, put my commas in there, we're going to say the same thing, is that the larger the wavelength, meaning, again, if I just use the number 10 as an example, the larger the wavelength of that signal, then the lower the frequency of that signal is going to be. And that makes sense to me because, we said that frequency is how often the peaks occur. So if I have a large wavelength, that means there's a larger distance between the peaks. And so my frequency, because it's not going to occur as many times in 1 second, then my frequency is going to get lower. And vice versa. I'll make another little chart. If my frequency is very high, then the distance between the peaks, the wavelength, is also going to get smaller.